Okay. All right, so let's continue where we left off. What I'm going to do is I'm going to do a quick recap on the homework assignment attached to this video. I want to make sure that you know how to do these problems. Okay. So the first set on the last video, remember when you're verifying, all you're doing is substituting this into x and making sure that that solution works. So for number 6, plug in pi over 3 in here. Number 7, you're going to do something similar. That's one way of doing it. Another way of doing that, let's take a look at number 7, just so I don't do your actual evens. I'm going to add 1. This is a multiple angle. Did I talk about multiple angles yesterday with you guys? No, I said I was going to do that today, right? Okay, so actually let me come back to that one in just a second since I didn't talk about that yesterday. Let's take a look at number 9. Number 9 here, this is factorable. So here we're going to write 2 sine x, and then the factors for 1 have to be 1 and 1, and in order to get a negative in the middle, I need a negative 2. So now that I have those, I can set each of those equal to 0, and I'm going to have 2 sine x plus 1 equals 0, and I'm going to have sine x minus 1 equals 0. Here, sine x equals 1. And where does sine equal 1? Well, that happens at pi over 2. So this would be the proof for A. And that's how you would do that. So you're just providing evidence that this is a solution. And how do I do that? For this particular problem, you have to factor. If you look at number 10, which is a homework problem, here you could factor out cosecant squared x. And then you have factors that you could set equal to 0. And then determine, is pi over 6 a solution? So that's how you do problems 5 through 10. All right, when you get to problems 11 through 24, there's different things that you could be looking at. So let's just entertain one at a time. Number 11, what you're going to do is you're going to add 2, divide by radical 3, and then determine where does cosecant give you that solution, okay? Or you can write 1 over sine and determine where does 1 over sine give you that solution. That's one way of doing it. When you get to something that looks like 13, what you want to do is you want to add cosine to both sides. And now you have 2 cosine on the left. So let me go ahead and move that over. So we get 2 cosine x plus 1 equals 0. And now I have something that looks like my slides from yesterday. Subtract 1, divide by 2. Where does cosine x equals negative a half? Well, cosine is negative in quadrants 2 and in quadrant 3, and it's specifically negative a half at 2 pi over 3 and at 4 pi over 3. And remember, in order to capture all possible solutions, you have to write plus 2 n pi. And make sure that you don't have an extraneous solution. How do you do that? You plug it back in, you check it. Okay? Number 15, let's take a look at number 15. You would do the same thing. You're adding 4 divided by 3, taking the square root of both sides. Number 17, add 1 divided by 4, taking the square root of both sides. Number 19 is a double angle. Let's take a look at number 19. Okay. So 19 is, we could call it a double angle, or depending on what's next to x, we could just refer to it as a multiple angle. So here we have a multiple angle. Let's put that aside for a second. So here's our multiple angle. How do I solve for it? I temporarily pretend that this just says x. Okay, so I'm going to solve as if that's x. So what do? I divide by 2 on both sides. Remember, that's pretend like it's x. And how do I get sine squared by itself? I'm going to take the square root of both sides, and I'm going to get sine 2x equals, and then when I simplify the radical, square root of 1 is 1 over radical 2. You have to rationalize your denominator, and you end up with root 2 over 2. And ask yourself, where does sine give you the solution root 2 over 2? Well, we know that happens at pi over 4, and it also happens at 3 pi over 4. And if I'm including multiple cycles, we would write plus 2 n pi. But I had a double angle or a multiple angle. So the multiple angle equals whatever that is. So now your goal is to get x by itself. So this is the only additional step you have for multiple angles. How do you get x by itself? You would divide by 2. Divide by 2. So the solution here is x equals pi over 8 plus n pi, and x equals 3 pi over 8 plus n pi. So here are the solutions for number 19. So that's the only additional step for multiple angles. You temporarily suspend it, and then at the end you say that multiple angle equals however you approach the problem, whatever it was, and then get rid of that multiple angle. Alright, so let's go back here. When you get to a problem that looks like 21, this is already 2 factors. Okay, so if I already have this broken up into a factor times another factor, I can break them up and say that those equal 0. So if I'm looking at number 21, I have tan, and it's also multiple angles, so this is good practice for us. X minus 1 equals 0. So tan of 3x equals 0, and tan x minus 1 equals 0. So now I have tan x equals 1. Well, where does tangent equal 1? That happens at pi over 4. And if I'm including all possible solutions, that's plus n pi, not 2n pi. Plus n pi. And tangent's also 1 at 5 pi over 4. Plus n pi. Here you have a multiple angle. Where is tangent equal to 0? Well, tangent's equal to 0 at 0 radians, plus n pi. And it's also 0 at pi. I meant to write pi, not 0 again. So pi plus n pi. And so now I have to just take that multiple angle into effect. So how do I get rid of 3x? I divide everything by 3. So the solution here is going to be x equals 0. Okay, so 0 divided by 3 is 0 plus n pi over 3. And our next solution is pi over 3 plus n pi over 3. Alright, going back to your homework, that's exactly what you're going to do for 23 and 24. It's already broken up into 2 terms that you can set equal to 0. And in the homework, since your homework's the evens, number 22, you would do exactly like that. Number 24, you'll do exactly like that. 20 is your multiple angle. Okay, isolate it. 18, I would use a Pythagorean identity. If you like cosine, switch sine squared to 1 minus cosine squared. If you like cosine, if you want to do it reverse, you can switch cosine to 1 minus sine squared. And then combine like terms and get cosine by itself. That's how you would do that one. Alright, in the next set of problems, we are on the interval from 0 to 2 pi. Here, there should be a bracket. We're including 0, not including 2 pi. So 2 pi is not part of our solution set. We're approaching it, we're not equaling it. So we're finding all solutions. So let's take a look at some odd ones. Alright, so let's take a look at number 25. So when I'm solving this particular problem, I want to bring cosine to the same side. Because these are the same, I'm going to bring cosine to the left. So I'm going to subtract cosine from both sides. And when I do that, I can go ahead and factor out a cosine. So I get cosine squared x minus 1 equals 0. And now I have 2 terms that I could set equal to 0. So let's go ahead and do that. So we have cosine x equals 0, and we have cosine squared x minus 1 equals 0. Well, where is cosine 0? Cosine is 0 at pi over 2. And it's also 0 at 3 pi over 2. And I don't want to go over 2 pi. Why? Because the instructions told me not to. And then in just a moment, we're going to go back and check to make sure that there's no extraneous solutions, that it works in the given problem. Here, I add 1, and then I take the square root, and I'm going to still end up with cosine equals 1. Well, where is cosine equal to 1? Well, cosine is 1 at 0. Now plug that back into the given. Here's our given. Okay, so we want to plug in pi over 2 here, 3 pi over 2 here, and 0 here and here. Okay, they all work. All right, here you're going to do exactly what we did here. Bring that tangent over, factor out a tangent. Let's take a look at 29 and on to make sure you guys are comfortable with those. All right, so here's the rest of it. If I were solving these problems, let's see, 29, I would bring that 2 over and factor, okay? For number 31, I would rewrite this as 1 over sine, get a common denominator, then factor. Okay, number 32, I would actually get rid of that 2 because if you add 2 to both sides, you get rid of them. And then if you square both sides, let's go ahead and do that. I'm going to get sine squared x equals cosine squared x. And now I can use a Pythagorean identity wherever I want to. I can either substitute this one, or if I wanted to, I could substitute this one. For the sake of the example, I'm going to write this. And then bring everything to one side. So I'm going to add cosine squared to the right just to keep it positive. So I'm going to have 2 cosine squared x. Divide by 2. And then take the square root of both sides, and we end up with cosine x equals root 2 over 2. Well, where does that happen? That happens at pi over 4. And that happens at positive cosine is 7 pi over 4. Okay? And then I'm on the interval from 0 to 2 pi only, so therefore those are my only solutions. I don't have to write that plus 2n pi. So again, your only solutions here, x equals pi over 4 and 7 pi over 4. Then you want to plug it back into the given, because notice that you had the given was sine x minus 2 equals cosine x minus 2. You want to make sure that this is part of the solution of the actual problem. So let's plug in sine of pi over 4. Well, what's sine at pi over 4? Root 2 over 2. All right, root 2 over 2 minus 2 is going to be the same as on this side 2. So that one's good. But 7 pi over 4, I said sine, and yeah, that's fine. 7 pi over 4, when I look at sine at 7 pi over 4, that's going to be negative. And cosine's still positive. The solutions are not matching. So this one's not part of the solution, just this one. So you want to make sure that when it looks different on both sides, or when you manipulated something, or your trig identities aren't the same, that it is working back in the original equation. Okay? So that's really important to do. Check your solutions. If I were doing number 33, I would factor that one. If I were doing 34, I would do the factoring on that one. Here, I'm going to substitute a Pythagorean identity just like I did here. So here I could substitute it for tangent, right? Or this one I could substitute for secant using the Pythagorean identity, and then go ahead and combine like terms. Here, you can rewrite tangent as sine over cosine, and you get sine squared, and then you can switch sine squared to cosine, and then you have something that you can manipulate here. All right, you want to do the same thing for these other problems. Use some of your identities to substitute it. All right, so here are these multiple angles again. I want to make sure you guys are comfortable with them. All right, so let's take a look at number 43. Because that one's a fraction, and I want you to be comfortable with the fraction ones when you get home. Let's just quickly look. It says solve the multiple angles, so it's not telling me on an interval, it's just saying solve. So that's saving us a lot of work, because multiple angles change the period. Remember I was saying that a moment ago? So if I'm listing all my solutions from 0 to 2 pi, I'm going to be listing them from 0 to 360 degrees. And if I switch that period, I'm going to be listing a lot of solutions. So fortunately, they're not saying that. They're just saying solve. So that means I'm just going to create a statement of plus 2 and pi or whatever it is. All right, so here, remember, treat this as if it's not there. Add root 2, and then divide by 2, and we're going to end up with this. And where does cosine equal root 2 over 2? Well, that happens at pi over 4 plus 2n pi. And where does cosine's also positive in quadrant 4, that's 7 pi over 4 plus 2n pi. And this time it's different from the other multiple angle problem I showed you guys a moment ago. Remember, the other one was 3x equals the rest of it. Here I have x divided by 2. So how do I get rid of divide by 2? I'm going to multiply everything by 2. So that's the only difference here. So everything gets multiplied by 2. Let's rewrite it. At top one we get x equals 2 over 4 is a half. And then 2 times 2 is 4. And the next one I get 2 over 4 again, so that's going to be 7 over 2. plus 4n pi. So fortunately for us, we switched the period. We don't have to list individual solutions, so this is sufficient. All right, so we're finally at the back end of what you're going to see in problems 46, 48, 60, 64. This is an example that you'll see for 46 and 48. Okay, so all I want you to do is determine where is this graph crossing the identify the x-intercepts. Let's roughly approximate that this graph is crossing it at 1, and let's say that's 2 3/4, 4 1/4. So in your text, this is exactly what you'll see. So it says find x-intercepts. In exercises 45 through 48, find the x-intercepts of the graph. So I want you to literally just look at it and determine where is this crossing the x-axis or touching the x-axis or any of that. Okay, so it's happening at -1 and 3. So that's all I want you to do, identify the x-intercepts. So this has a solution at -1 and at 3. Okay. All right, I'm reversing examples 5 and 4 on purpose. So let's take a look at example 5. It says use inverse functions to find all solutions of the equation in the interval from 0 to 2 pi. All right, so we're going to use inverse functions. So that means I'm using, in context here, it's going to be arctan, right? Remember that? And we're on the interval from 0 to 2 pi. So if I were solving this problem, I would solve this problem by factoring. And the factors for 12 are 4 and 3. And I want the positive middle term, so the bigger number has to be positive. And then I can set them equal to 0 now that I have two terms. And here I get tan x equals -4 and tan x equals 3. All right, well that's clearly outside of the scope of the unit circle. Because it's outside of the scope of the unit circle, that's why the instructions say use inverse functions. Okay? So now if I'm just rewriting using an inverse function, I'm just going to introduce the word x equals arctan -4. And x equals arctan 3. All right, so keep in mind that we're only on the interval from 0 to 2 pi. So I'm going to use my calculator to help me at this point because I don't want any so think about 0 to 2 pi means 0 degrees to 360 degrees. I don't want any negative degrees or anything above 360 degrees. So I'm going to use my calculator to help me find these solutions. So let's, to our calculator, degree mode I think is the easiest way to picture this. So switch your mode to degree mode and do arctan -4. And you're going to get -75 degrees, or -76 if we're rounding up. That's clearly outside of the interval from 0 to 2 pi. So this cannot possibly be part of the solution because it's outside of the interval that the instructions asked us for. But the moment I do arctan 3, now I'm in range, I get 72 degrees. But the solution said, remember that if I'm listing all possible intervals, or all possible solutions, oh, I meant to write n pi. It's plus n pi. So if I'm adding 180 degrees to 72, I'm going to get 252 degrees. So I really have two solutions here that are happening here. So my only solution's coming actually from this one. All right, last example says use the quadratic formula to solve the equation in the interval. So we're seeing this concept of in the interval again from 0 to 2 pi. And then use a graphing utility to approximate the angle. So I already kind of introduced the approximation of the angle. Again, we're going to use arc, in this case, sine. In the previous example, it was arctan. So in this one, ask yourself, is it factorable? The answer is going to be no because it's clearly telling us to use the quadratic formula. So remember, x equals -b plus minus the square root b squared minus 4ac all over 2a. And this is problem number 60 in your homework assignment. Okay? So this is A, this is B, this is C. Now I'm doing direct substitution. So if I want to, I'm going to write sine of x equals -b, -13 makes it positive, plus minus the square root of b squared minus 4 times a times c, all over 2 times a. 2 times 12 is 24. And then that's going to equal 13 plus minus 169 minus 144 over 24. And what we get here, we get 13 plus minus the square root of 25, which is 5. Over 24. And our solutions are as follows. So let me zoom in over here. We get sine of x equals 13 plus minus 5, I said, right? So 13 plus 5, 18 over 24. And then 13 minus 5, we get 8 over 24. 18 over 24, I get 3/4. And 8 over 24, I get 1/3. Good. All right, so now I have solutions that are clearly outside of the unit circle again. So that's why we're going to approximate using our calculators. Again, we're going to use the concept of inverse function. So x equals arc sine 3 over 4. And x equals arc sine 1/3. And for the sake of this example, let's just keep it in degree mode so it's easier to imagine. Okay? And so that way it's easier to understand that we're staying under 2 pi, under 360 degrees. So arc sine 3 divided by 4. Remember, because it's plus 2n pi, I want to keep adding 2n pi to the cycle if I need to. But I won't need to. This one's 49 degrees. I'm rounding to the nearest degree. Arc sine 1 divided by 3. And we got 19 degrees. So clearly if I add 2 pi to that, I'm going to be over 2 pi. So these are the only answers I have, okay? And if you want to switch that to radians, I'm fine. I only put in degrees so you can understand the concept. And again, this is how you do number 60 in your homework.